All right, well that sounds like the bell's been rung, so we'll go ahead and get started here. So my name is Stannard, and I'm one of the co-founders of the Akka.NET project. And today we're going to talk a little bit about Akka.NET, actor systems, and the future of distributed computing in .NET. So quick show of hands from everyone in the room, who's actually used Akka.NET before? All right, so we got a little bit. Who's familiar with the actor model? Who's heard of that before? Quick show of hands. A bit bigger group, great. And who's currently working on what you would call like distributed systems development today? Quick show of hands. All right, cool. Sort of wanted to get a little level set for sort of who's attending today. So I'll tell you why you should care about anything that I'm going to say over the next hour or so. And that's that if you're a backend developer today, the expectations for you and what you are expected to deliver at work have never been higher than they are right now. In the big data space, there's this phrase called the 3 V's you have to worry about. So the first one is velocity, which is that the amount of work our servers are expected to do is increasing in terms of the amount of requests per minute or requests per second we have to serve. So the velocity with which people are beginning to access our services and the way in which they're beginning to use them is increasing all the time. The second V is the concept of variety. And what we're referring to here are the variety of different experiences people want to have with our backend services. So a couple of good examples of things we have to do today we didn't have to 10 years ago. We have to service mobile clients now who want access to their data in real time on a device that has much more limited bandwidth than what you normally get from a desktop or a laptop. So we have to cater an experience to suit them as well as our existing sort of web clients too. Another example of variety. Who's using SignalR today? Quick show of hands. The real-time web is a totally new type of experience that's only really been possible for the past 5 years or so. And that's yet another class of experience we might be asked to deliver to our end users at some point. And then the last of the 3 V's we have to worry about is volume. So there's velocity, volume, and variety. Volume refers to the sheer amount of data we're expected to use, retain, and analyze in order to produce the most value for our end users. So we're expected to maintain a system that can be available during all 3 of these sort of increasing demands on us with no downtime at all. And so what all this amounts to is that a chief concern that backend developers have had to get acquainted with over the past 10 years or so is the concept of scalability and availability. And what I'm going to tell you in the next few minutes here is that the reason why technologies like Akka.NET and the actor model are taking off is because the obvious ways of achieving this are all inherently wrong. Let me give you some examples. So your traditional CRUD application has followed this sort of design over the past 10, 20, 30 years. You have a load balancer that round robins some requests to a couple of web servers. Then you might have a private zone with a SQL database sitting in it. And that might have a slave that it can fail over to. You might have a little OLAP process that goes and grinds out all of your business intelligence and analytics. And then you have your internal line of business applications that all consume that data for the different business units in your organization. So your analysts, your marketing team, your finance people, your sales folks, et cetera. So this is sort of what the traditional architecture has looked like even today for your typical enterprise application. Well, let's take a look at how some of the different changes in velocity, volume, or variety might put this system under stress. So based on this diagram, if we experience a giant surge in user activity, so we experience an order of magnitude increase in the velocity of the requests that we're handling at any given moment, which part of this system is going to be your bottleneck? Shout it out if you know the answer. SQL Server. All the arrows are pointing there, so it's pretty obvious that's going to be where the problem is. Well, the obvious solution for scaling this problem is to do what? Throw more hardware at the problem. We're going to use sharding. So the idea behind sharding is we take the same master-slave system that we had running one database and one slave, and we run multiple copies of it in parallel. And then we have a router or coordinator help us partition data equally amongst the different shards. So if you're partitioning data that belongs to your customers, you might shard by the first letter of their last name. So shard number 1 here might have customers A through D. This might be E through G, etc. And then we have all of our actual clients, in this case our web applications, all connect to the coordinator so they can get their requests routed to the right shard. So this is the obvious way of trying to solve that bottleneck problem that we're going to run into as our volume and as our velocity increases. Well, there's a couple of issues with this design. The first is that downtime is inherent in this model. If a master goes down, one of the new slaves needs to be elected to become the new master. What's going to happen during the period in which there is no master for all those requests? Any guesses? Anarchy. They're all going to be failed. So any requests that attempted to go through during that period of time to that shard will all be unavailable. But that's not the most insidious problem. The real failure of this design, and this was state-of-the-art like 2003, 2004, is the fact that it's brittle. Who's familiar with the concept of a network partition? Quick show of hands. All right, well, this is what a network partition looks like. So imagine there's a hardware switch in your on-premise data center that fails briefly. It might only need to be down for a handful of seconds in order for this to happen. These masters can't communicate with their slaves on the other side of the partition anymore. All the servers are still running, so there's no machine that's down, but they just can't contact each other. What do you think is going to happen when these slaves can't see their master anymore? We're going to end up with 2 masters for 1 shard. This is a specific type of network partition known as a split brain, is the name of this. And it's the most dangerous type of partition because most of the time, if you don't have good monitoring tools, you won't even know that it happened because it's a software error. It's not a hardware error. So what can happen when you have a split brain is data corruption. So imagine you're using like auto-incrementing IDs in SQL Server. Well, one record might go to one master, and another record might go to the other. They both have the same ID, but they're totally different pieces of data. So that's data corruption. Data loss is also possible. So this is a pretty dangerous design. But this was the obvious way to try to scale that system we had before. But its weakness is that it can't detect and handle partitions very well. Now, another scenario, we're going to look at the variety aspect here. Let's say you get asked to take your existing application and add a component of real-time user interactivity to it. So here's the little data flow for what that might look like. User generates an event. Let's say it's a click stream on your website. So someone's clicking through buttons and links, and you go ahead and record an event for each one of those. If a user produces 4 particular events out of a possible set of hundreds of thousands, you want to send that user a specific message. Maybe if you're running an e-commerce site, you check to see if a user has clicked on these 4 products, and if they have, you offer them a 5th one that might be related to them. That's one example of how this might look. If a user hasn't produced those 4 events, you just want to keep waiting and try to observe in real time, are they going to do it or not? And I had to actually build this system in production to handle hundreds of thousands of users simultaneously. And this is part of the origin story of Akka.net too. So the obvious solution to this problem is to keep using our database that we had before and use a strategy called read after write. So we have our same little hardware setup, and here's what we're going to do. A user is going to produce the 4 events we're looking for. So we go ahead and write the first event to our SQL database, and then we read what are the range of events that have been written back out. So we write 0, we read 0 back. We write 1 on the next server, we read 0 and 1 back, and so forth. Until eventually, when the 4th and final event is written, we read back the full set of events we are expecting and fire off our notification. Now, the way this actually works in the real world, if you try this design, which I did, is you can't actually predict the order in which anything on the network will happen, even under ideal circumstances. Your database can't be responsible for the level of concurrency that's happening above it in the application layer. So the truth of the matter was, even with very high consistency settings, if I went and started writing events and reading them back out, I'd get totally different results back than what I expected. And so the truth was just frustration was all that I got as the fruit of my efforts here. So read after write is not a practical solution for doing real-time user interactivity. And the other reason why it doesn't work very well is because it's slow. Round-tripping to a database incurs network I/O overhead, disk I/O overhead on the database layer, serialization overhead in both directions, and on top of that, you usually have some I/O completion port overhead too. And all that adds up to be something that may not necessarily work very well quickly at scale. So these are the sorts of problems that we're being asked to deal with, and the obvious ways of solving them don't work. So distributed programming is hard for the following reasons. The first is dealing with state. That was fundamentally what we were trying to do in the last diagram, was we were trying to build a stateful application that could observe a stream of events and react appropriately. Dealing with state in a web application is hard because why? Who can guess? HTTP is a stateless protocol. It makes it very difficult to guarantee your state ends up in the right place in the network. So that's one reason, and we'll explore a couple of others too. Next is concurrency. Raise your hand if you think shared state concurrency with locks, semaphores, critical regions is easy. Good, that's the correct answer. No one. Concurrency sucks. It provides tremendous benefits, but doing it right is hard. At least it used to be. Next is topology and discovery. Both of those architecture diagrams I showed you earlier followed what's called a tree architecture, where you sort of have your load balancer at the very top of the tree, then one layer leaf nodes are your web server, and then you have your database server underneath that. None of your web servers know about each other under the load balancer. As far as they know, they exist in isolation from everything else. That lack of topology awareness makes it very difficult to deal with state appropriately in a distributed system. That's one problem in and of itself. The other is discovering who's available to do work in your network. It's not only knowing like which addresses should servers be at, but who is still there, who's died in the past few minutes, who's come alive again, that sort of thing. We have a module in Akka.net called Akka.cluster that deals with this problem very specifically. Next is recovering from failures. So you've probably attended maybe a microservice talk before, and they talk about this notion of fault isolation. That's one category of problems you have to deal with on the network, which is what happens if one service crashes. You want to have some sort of partial failure mode so the rest of your application can continue. What about more insidious types of problems like that network partition? What happens if those services aren't completely unavailable? They're just not reachable right now. How do you deal with that appropriately? Or how do you deal with more localized failures? Like what happens if one particular stateful entity in your system suddenly crashes as a result of a software failure? How do you heal from that and recover? Well, the actor model has an answer to that. Next is bottlenecks. So people like these sort of master-oriented systems like SQL Server because conceptually they're easy to understand. There's one node who dictates what the right answer is for each transaction. It's pretty easy to follow. But what you give up in order to do that is you give up the ability to scale linearly. You're stuck with this one sort of bottleneck node that has to be there at all times in order for you to be available. And as soon as the load on your system exceeds that node's capacity to stay up, you have a problem. Then on top of that, there's the matter of consistency. This means all nodes seeing the same data at the same time. Now, the truth of the matter is, once you have more than 2 computers in a network, it's not possible to have perfect consistency. The speed of light is your minimum bound there. But you do have to keep in mind sort of what levels of inconsistency can you tolerate temporarily from nodes. This is the concept of eventual consistency. That's another issue that we have to deal with. And lastly, there's availability. This means the ability to stay up and be able to successfully respond to requests. So you have, for a service to be available, it has to be able to go ahead and return the equivalent of like HTTP 200, something like that. These are all hard problems in and of themselves. What I'm going to tell you today is that they're hard with the tools and what we've been used to using as web developers primarily. We have to look at these problems from a different perspective, and they become a little bit easier to manage. So what we're going to use to sort of solve some of these problems today, First is we're going to embrace state. State is no longer a bad thing, and it's not going to live in our database anymore. It's going to become part of our application. Next is we're going to embrace a concept known as protocol-driven design. These are ways of building distributed systems that plan for a failure as an eventuality. It's not something we sort of stick our heads in the sand and hope to avoid. We go ahead and basically anticipate the failure of the network as something that is inevitable. And we factor that into the design of our protocols. Fault and resource isolation is another thing we're going to use. We're going to come up with a strategy for dealing with failures locally, so they don't become some problem that a central coordinator node has to handle. Decentralized architectures are another thing we're going to look at. This means no more masters. Actually, the right way to really phrase what a decentralized architecture is it's a peer-to-peer network, but on the server side. That's what that is. And then the CAP theorem. This is our decision-making framework we're going to use for deciding what sort of compromises need to be in our distributed system in order to fulfill our business requirements. So these are the consistency, availability, and partition tolerance. Now, one thing I'm going to state before we dive into the gist of what the actor model is and how it helps with these issues is that don't assign any moral weights to any of the CAP categories. I meet a lot of DBAs who are turned programmers now who think consistency belongs in like an altar above the other two. It's not true. They're just different currencies you have to balance in the design of your system according to what your business requirements are. So enter the actor model. This is going to be the tool that we're going to use to try to address some of these problems. The actor model dates back to the early 70s. The original actor model white paper by Carl Hewitt is only a couple of years younger than the original relational database white paper. 1973 is when the original actor model white paper was written. So it's a fairly old concept. And where the actor model originally came from was this vision in the 1970s of how big servers are going to be designed. It was going to be a single machine that had thousands of very small CPUs built into it. So lots of 486 processors and that sort of thing. And that's not how reality turned out for how computers are going to be designed. Moore's law saw to that. Instead, we have servers that have a relatively small number of cores, maybe as many as 64, rather than the thousands that Carl Hewitt and his team were imagining. And they are much more powerful than anything that was imagined back then. But the actor model sort of found its place in the late 80s and early 90s when we needed to develop some modern telephony software for the first digital networks. So Ericsson had an engineer named Joe Armstrong who was tasked with developing some software to handle these sort of modern data networks. Think of it as like a big backplane for handling all the phone calls, not text messages, but other types of data packets that would be going through the network. They had to come up with a system for routing all this. This is the original web scale sort of problem back in the day. So Joe invented a commercial implementation of the actor model known as Ericsson language, later renamed to Erlang. So this is the real first implementation of the actor model that was really accessible by developers. And it allowed them to build telephony networks. But a little bit later, let's say we jump forward 10 years to the first .com boom, where Erlang and the actor model saw some action again, were some of the first really big publicly traded online companies doing things like real-time advertising networks or doing multiplayer games, that sort of thing. Those models were all pretty naturally suited to the same sort of design concerns that Erlang had. Namely, you have massive concurrency, so millions of operations happening in parallel across the network at once. But you also had this sort of real-time component to it. How useful would a telephony system be if it delivered all of your voice packets in batch 30 minutes later? It would be utterly useless, right? It'd be like AT&T in the United States. Sorry, I always make fun of them. They didn't deserve that. But the gist of it is all these systems had these sort of real-time concurrent scaling issues that they had to solve. Well, jump forward another 10 years to the advent of cloud computing. A lot of the applications you work on, whether you're in insurance or e-commerce or healthcare or doing Internet of Things, which is a category that didn't even exist all that long ago, you're all subject to a lot of the same sort of forces that these other older applications like the telephony networks and advertising systems all had to deal with 10, 20 years ago. The difference is today that the actor model is now available on more runtimes. There's Akka on the JVM. Akka.net on the CLR. And if you attended the Orleans talk earlier today, that's another implementation of the actor model. So here's the core concepts that make the actor model simplify a lot of these distributed programming problems I spelled out earlier. The first is that actors are a fundamental unit of work and concurrency. You can think of them as sort of a self-contained little microprocess. All communication between microprocesses is done via message passing, kind of like how IPC would work with a normal full-blown Windows process. So these are how actors communicate. All messages that actors share are immutable, and there's a very important reason for that we'll touch on. And next, sender and receiver are always decoupled from each other and are fully asynchronous. So when you tell an actor a message, you don't get a task back in Akka.net. That doesn't mean it's not asynchronous. Just that we typically don't give you a handle back for waiting on when a message was received. Because a lot of what Erlang and the sort of original actor model implementations try to encourage are things like one-way messaging, because they're fast and they're cheap. Next, in terms of what actors can do, they can process messages. Actors do work by chewing through the contents of their mailbox. So these are all the messages that have been sent to them, sit in a little queue that the actor processes. Actors can also spawn other actors. And in Akka, this concept is known as sort of like a family tree. When I create an actor, I'm creating a child of myself. That actor can go on to create its own children, and so forth. You can have these sort of hierarchies that go several layers deep. Actors also have the ability to change their behavior between messages. So imagine you have a bunch of what are called receivers, little statements you declare specifying how to handle certain types of messages. You could switch those depending on the state of your actor. So this is where the concept of a finite state machine comes into play. So here's a good example of a finite state machine as far as actors are concerned. Let's say you're building a chat system, and you had an actor represent every user who is trying to connect to your chat server. That user could be in one of three possible states at any given time: unauthenticated, authenticating, or fully authenticated. In the unauthenticated state, do we want to allow that user to send messages to the chat room? No, we want to discard them. If a user starts to authenticate, we transition to an authenticating state. And let's say a user tries to send some messages to the chat room then. What do we want to do with those? Maybe we want to buffer them and hang on to them in case the user successfully authenticates. Then we can deliver them. And if a user is fully authenticated, we just want to deliver the message at that point. That's an example of behavior switching in action. The last thing actors can do, and this is key, is they can contain private state. Actors can have their own internal members and data structures that they use, and you can use those to accumulate state inside an actor over time. This is what makes actors effective for building these sort of stateful systems. Now, actors also make some promises too. The first promise, and the most important, is that actors only process one message at a time. So if they have a queue of messages in their mailbox, they're only ever handling one of them at any given time. Next, those messages are always processed in, first out order, otherwise known in the order in which they're received. So actors make a guarantee that's how they'll process their messages. Now, you as the developer using Akka.net can modify that. For instance, we have this concept known as the mailbox. This is where actors queue their messages. That can be overridden by you as the developer to use a priority queue if you want. So you can prioritize certain messages ahead of others. The last guarantee that actors make is at most once message delivery. So when we have an actor send a message to another, that's it. By default, we don't go and check to see if that message got delivered. The reason why that is because the core Akka philosophy is to be extremely dumb and fast. So the reason why we do that is because we view Akka as infrastructure. We don't try to guess what you want to do as the end user. You explicitly tell Akka what you want. Our philosophy is that it's a lot easier to add intelligence where you need it than to go through and turn it off where you don't. That's the reason for that philosophy. The last thing is that every actor, even in a big network where you might have millions of actors and thousands of servers, Every actor has a globally unique address, their own unique URI you could use to send them a message. But typically, you don't need to know what that URI is. The way you communicate with actors is through a construct known as an actor reference. It's a handle to an actor. Now, I'm sort of spelling all this out now before I go into detail on each subject. So if you're worried about all the information, don't worry about it. We're going to cover it a little bit more extensively as we move on. So these are all the core concepts at work here. And I'm going to spell out for you sort of how these give you some benefits for being able to build these distributed systems. So Akka.NET gives you all this for .NET. And Akka.NET consists of a handful of modules. We're going to be spending most of our time talking about the core actor library, which is Akka. This gives you all of the core actor functionality, all the ability to send messages, the ability to go ahead and have actors that are stateful, actors that can run on the UI thread of a Windows Forms application, that sort of thing. So that's what the core Akka library gives you. Akka.remote gives actors the ability to communicate with each other across different Windows processes on the network. So that's sort of the next layer up when you want to start doing some networked work with actors. Then we have Akka.cluster, which is a module that gives multiple Akka.remote nodes the ability to form a decentralized network with each other. Then we have Akka.persistence, which is a library that allows actors to use event sourcing to record their state to some durable store. And we support like 12 different databases right now. Everything from SQL Server to Cassandra to Event Store to RavenDB, I've even seen out in the wild. So there's a lot of different targets we support for that. If you have questions about some of the other modules on here, I'll take those at the end. Now, what's an actor actually look like? This is an example of what's called an untyped actor. It's just a class that inherits from this untyped actor base class. So there's multiple different base classes that Akka.NET exposes. Untyped actor is the dumbest. It does the least amount of work for you. Typically in production, I use an actor that's known as a receive actor. This gives me these sort of typed predicate functions I can use for matching messages. In C#7, when we get pattern matching as a sort of first-class language construct, you'll probably see the untyped actor get used more commonly again. Now, the most important method on this class is this one, onReceive. Every time an actor receives a message, when the actor is ready to process that message, it'll be handled inside that method. And typically what you do when you receive a message is you do some work. So that might be maybe making a web service call over the network. Maybe it's doing some sort of validation. Maybe it's just transforming the message into some new type of object and sending a reply back to the original actor. You could do any number of things. But that's the most important method. The other ones up here, pre-start, pre-restart, post-stop, and post-restart, these are what are called lifecycle methods. These are built for having an actor initialize certain resources it might need when it first starts. So you might put that in your pre-start method. Or imagine what would happen if an actor threw an unhandled exception. If you had a process crash on your Windows PC, what would you do with it? Or what would you hope the process would do if it was critically important? Restart it, right? One of the things that actors do is they have this philosophy of when you run into an unhandled exception or some type of failure, you're much better off just letting the actor crash and restart back into its initial original state. And the reason for that sort of philosophy is this idea of all of the error handling code you typically have in your application. How well tested do you think that is? It's typically in the area where if you're using .cover, it's typically in the area with all the red highlighting. That error modes and fault paths typically aren't covered very well. So rather than try to go and come up with these intricate and typically brittle error recovery systems, why don't we just go ahead and reboot the components of our application that faulted back into their original safe state, the state they were when they failed. And that's the Akka philosophy behind how we typically handle failures, is just let it crash, let it restart. And so with actors that are using things like Akka.persistence, the original state of that actor will include whatever its last recorded state to the database was at the time it crashed. And actors don't lose their messages when they crash either. As you'll see in a moment, the mailbox, which is the sort of queue that holds the actor's messages, is separate from the actor's state itself. So we'll go ahead and destroy this simple actor instance and replace it with a brand new copy of it when we restart. So that's sort of how the actor lifecycle works in those sort of failure states. Now, when it comes to actually dealing with state and being able to manipulate it sort of concurrently in a distributed system, actors really simplify that problem pretty dramatically. So internal state of an actor looks just like any other normal .NET object. It's just some field or a property that you set inside an actor. No more complicated than that. Now, what's interesting about this state is that it's always designed to be private. Actors don't expose their state as a property that anything can go and access anywhere else. Moreover, that simple actor instance we saw earlier, when you start that actor, you can't get a reference to that object anymore. It's hidden inside this sleeve known as the actor cell. This gives us a layer of isolation from other processes in our system in order to make sure that actors can experience what's known as a side effect. Who's heard of that before, that term, side effects? Cool, it's about a third of the room. A side effect is what happens in a concurrent system where one process modifies another state of something else that process B is depending on. We try to avoid side effects. That's how you end up with unpredictable behavior in a concurrent system. So actor state is private, and it's only ever shared or modified by sending messages or receiving them. So actors, when they go ahead and build, sort of flesh themselves out, live in this family tree structure. You have a root actor. In this case, this is a built-in system actor called user. This will create some top-level actors. And then we have some children underneath them. So this is sort of what an actor construct looks like in production. And here's what's kind of interesting about this, is that every single actor's address, its unique URI, is a composition of who is above it in the family tree. So this grandchild has the name of its parent baked into its address. And so the way Akka tends to work itself is there's no central registry or coordinator node that keeps track of where all the actors are. All the information is decentralized into very small bits. Only this actor knows who all of its children are. And so whenever we want to try to deliver a message to an actor via its address, we sort of recursively iterate down the tree until we find the correct actor. This is designed to help allow Akka.NET to be very lean and memory efficient, is why we do that. Now getting back to this idea of processing messages, I mentioned that actors have internal state, and they're considered to be a fundamental unit of concurrency. The big goal of the actor system, from the point of view of just concurrency in your application, is to allow you to have state inside your app with no locks, no critical regions, no synchronization mechanisms, and no contention. And the way we achieve that is through our one message at a time processing guarantee. So imagine this sort of initial state of the system. We have a mailbox with 3 messages in it, and an actor, and then this sort of sleeve right here represents the actor cell. The actor will begin processing message 0, and at that point in time, maybe another message, message 3, gets queued into the back of the mailbox. Message 1 does not get processed until this actor's onReceive method exits. Once it does that, the next message will begin getting processed. So, quick question for someone in the room to answer. If an actor can only process one message at a time, and that's guaranteed by the system, if we modify the state of our actors when we're processing messages, what can never happen if we're only processing one message at a time? The state can never be modified concurrently. It's safe. All actor state is inherently thread safe. This is what allows us to build distributed systems that can be stateful and can avoid all the classic pitfalls of shared state synchronization. What you do is you divide your state across a large number of actors, each one holding on to only a tiny fraction of it. What people tend to do, if we go back to the previous diagram, what people typically tend to do when they're modeling an actor system is, let's say you're building an e-commerce application. You might go ahead and model a sort of actor hierarchy like this. Well, let's say this part of the hierarchy represented all the products in your catalog. And you wanted to have one actor represent each piece of inventory you're carrying. So this actor might represent all the total inventory for one product. Then it might have another sibling named after another product and another like that. And you tend to sort of flesh out your state across a small number of actors that all have the exact same code, but they represent different entities. This allows you to write code that is very simple and easy to follow, but also scales beautifully in production. So let me step back through here. Now the next thing. Unfortunately, actors are not magic. They do run on threads. So the way actors tend to work in production, oops, sorry, I just realized I forgot to start the timer on here. The way actors work in production is that they typically split time across threads. But that's sort of done under the covers without you needing to know about it. So A1, in this case, going on core 1, might have a message to process, and so might A2. And they'll go ahead and go through the core and finish their, basically they'll finish their processing. They'll have finished a run of messages. Typically an actor will do a batch of like 30 messages or so each time they're scheduled. And they'll go ahead and yield the thread to the next actor in line. And so then the rest of the actors might go through and continue processing. And you'll see A1 gets scheduled again to execute. So actors share threads. The reason why I mention this is that in order to process one message at a time with an actor, we still need to use a thread. But what we do is we basically guarantee that for a brief period of time, an actor can hold on to a thread, whether it's in the TPL thread pool, whether it's running on the UI thread, if you're using a synchronized dispatcher. The actor will go ahead and basically complete a run of messages and then yield and wait for the rest of the system to go. So these are how actors fundamentally work. So I'm giving you all this as background to talk about just the concurrency and state part of distributed systems so far. We haven't touched on any of the other major classes of problems we've described yet. So one thing that's really important to note about Akka actors is that you don't necessarily need them just for building distributed systems. There's lots of folks who use them in client-side applications, and even some folks who have them running on Xamarin, Android, and iOS right now, for basically just handling UI events that might percolate up concurrently. Akka scales down to support that use case as well, too. Now, when it comes to the network, we deal with messages as sort of the primary way actors communicate. Messages versus, so there's a couple different ways you can think about communicating over the network. Most of us are web developers, I'm assuming, in the room. And the primary way I think a lot of us tend to think about the network is in the form of like RPCs, remote procedure calls, where I'll go ahead and send an HTTP verb and some state to a web API method, and I expect some response back. So these are these sort of request-response driven systems. Messages, when you work in message-oriented programming, and this is the sort of thing you'd get with actor systems or with a message bus like RabbitMQ or nService bus, these allow for a couple of different modes of communication you can't normally achieve with just plain old RPC. So messages are always comprised of two parts, the payload and the reply to address. The actor that sends a message to someone else on the network might not be the same actor that gets the response back at the end. This allows us to decouple who the sender, the receiver, and the final destination for a response might be, and allows for some communication patterns that are a little bit more flexible than what we're used to with RPC. Message sending is always asynchronous. The other thing that's cool about messages is they can be serialized and stored. So one of the reasons why we use event sourcing as the model for allowing Akka persistence to work is you can have a persistent actor decide to journal messages it's been receiving as part of its state. When it needs to rebuild its state down the road, what does it do? It deserializes those messages back out of the database and replays them during a recovery phase. That allows it to go ahead and rehydrate its state back up from nothing. So these sort of message-driven systems over the network play very nicely with that as a persistence model. Now, the other thing that's cool about messages is you can exercise what's called a deferment of processing a message. So that finite state machine example I had earlier. Remember when I mentioned that during the authenticating state, we might want to buffer some messages until we get the reply back as to whether the user successfully authenticated or not? That's an example of a deferment. We're deferring processing of those messages even though they arrive first because we're not in a state where we can handle them properly yet. This gives us some more flexible message processing capabilities too. You can't really defer processing of an HTTP request. You have to serve it and move on so the client doesn't time out. The actor model allows for more flexible modes of communication than that, which is another reason why it can help us solve some of our network topology and communication woes. The other thing we can do with messages is we can delegate who executes them to someone else. One of the things you typically see in these actor hierarchies is the parent actor, closer to the top of the hierarchy, usually delegates processing of messages to its children. So you tend to see these sort of messages trickle down from the top of an actor hierarchy down towards the bottom. That's very common. And the last thing you can do with the message is you can do broadcasts or multicast messages, where a message can be sent to multiple parties for processing. So a good example of that is in a couple of systems I've helped some Akka.NET users design. They have to have control messages. These are particularly true for some of our IoT customers, where what they need to do is be able to send a kill message out to a number of devices when a controller goes down. This is part of a safety regulation. We have people using Akka.NET in the oil and gas industry, for instance. Being able to go and broadcast that and confirm that everyone received it is a very useful communication pattern in that sense. So these are all types of more flexible modes of communication you can get with these message-driven systems that you can't very easily do with RPC. What this allows us to do is use some types of messaging patterns we can use to communicate over the network. So broadcast is one example. One node can take the same message and broadcast it to multiple destinations. Proxy is another example, where a node can go ahead, and by the way, node in this case can also mean actor. I'm sort of using the term interchangeably here. I can basically proxy the message down to a different node than who originally received it, and they can fulfill the request and reply back. This allows for more flexible types of routing in our system. Pub/sub is another great example. So we can have a couple of nodes subscribe to a publisher who will go ahead and notify them when a message of interest arrives, and then they can go and do some work with it. The way people tend to design a lot of big-scale actor systems is they have lots of little layers of pub/sub they use to construct a protocol. And that allows the system to be very reactive, where an actor at the top of the publishing chain receives a message and causes the sort of cascade of work to flow down from it. Those systems are very easy to design and debug. That's why this pattern tends to be popular. And then my personal favorite, because it's fast, one-way messaging, where I go ahead and it's like fire and forget messaging. I send a message and I don't care what happens to it. I used to work on analytics systems, and the majority of our communication looked like this because it was too expensive to build in request response. So these are types of communication patterns you can use between individual actors. What this allows us to construct are proper messaging protocols. The way you want to treat with issues over the network isn't by thinking about the design of specific actor classes or the design of specific messages. Rather, you want to design a protocol for communication between actors that can account for failure. So this protocol I'm about to show you, I think, is a consensus protocol. I think that's what this example is. Where a write comes into one actor, and this actor needs to coordinate with some replicas of itself over the network. Hey, are all three of us in a state where we can accept this write? Is this a valid and consistent thing we can do? And if the other two nodes reply back with yes, then we can go ahead and commit the write in all three places. This is designed to achieve a measure of consistency in all the data that's being modified over our network. The reason why I show this as an example is this is the way people think about designing systems with actors. There could actually be a whole hierarchy of actors underneath any one of these nodes participating in fulfilling this operation. But that detail is abstracted away from the protocol itself. If you treat the protocol as your specification for how individual actors talk to each other, whether they're local or over the network, it gives you a very flexible design. So I haven't shown this yet, but how actors actually talk is they communicate via reference. So this is an actor system. This is the sort of shared namespace actors use for talking with each other. It sort of provides a little fabric, a context that they can use for naming themselves, for being able to go and address other actors on remote systems, etc. Then we go ahead and we actually create an actor here. So this will be our little greeting actor. And we're giving it a name, greeter. When we want to have an actor actually process a message, we get this thing called an actor reference back right here. And I can tell the actor reference any arbitrary .NET object. And that object will be delivered to that actor regardless of where it is on the network. This is because this actor reference object has an important property known as location transparency. Who can name something you use every day that also has a transparent location? Well, I've got an example on the slide. Your cell phone number has a transparent location. So if I want to give my best friend from childhood a call, he's in Washington, D.C., and I'm here in Sydney. I don't need to tell AT&T how to manually route all my voice packets to him in Washington, D.C. I just need to know his phone number. And his location in the world physically is transparent to me as a detail there. Another example of something that has a transparent location is the domain name system. Imagine a world where you had to manually memorize all the IP addresses for Google Home servers. That'd be pretty awful, right? The DNS system helps make the location of where those servers are in the world relative to us transparent. And the load balancer sitting beneath those does the same thing again. What the idea of location transparency is really about is being able to go and interact with systems without needing to explicitly program in your code, whether they are a local or a remote system. So this code I showed you in the previous slide, I could specify in HOCON, the configuration format that Akka.NET uses, that this actor is actually going to live on a remote process in another data center. This operation would still work, even if that actor lived on a totally different machine thousands of miles away. Might take it a little bit longer to get my message, but it would still work. And the reason why this is a good thing for building distributed systems is it solves the problem of topology. If you don't need to care where an actor is on the network in order to interact with it, it makes it very simple for you as the developer to go ahead and build an actor system that implements a protocol for achieving some goal without having to worry about editing configuration files or without having to go and spin up a bunch of machines to test it. You can design code that works locally and expect that to still work over the network, as long as your protocol is designed to account for failure. So in an Akka.NET cluster, what you tend to have is you have a number of different, these are actual, let's say these are servers, for argument's sake. These servers can each have actor systems that have hundreds of thousands of actors in them in memory at any given time. I could have an actor on system A get a reference to an actor on system E, and it can send a message back to it without needing to know that node E even exists. Under the hood, Akka.cluster and Akka.remote give me that transparent location on the actor reference. And that's all I need to worry about. I just have an actor ref and I send it a message. So this is the next big thing that Akka.NET actors give us, is the ability to go ahead and transparently extend code that works locally over the network. It's not magic, just good design. One of the other things that helps us ensure that's possible is each one of these connections here. So these are Akka.remote associations, is what these are. In order for them to work and preserve all these actor model guarantees I showed you earlier, one of the things we have to do is preserve message order on the wire. So messages written from node A to node E also obey a FIFO ordering. So that means that any actor on node E receiving messages from node A will receive the messages in the order in which that actor on node A sent them. That's guaranteed by the way the framework is designed. Now, let's talk a little bit about state one more time. Of these two architectures I have on screen here, we have this sort of stateless app that does request response to a database server, whereas we have a stateful application server that has all the same information, but it's available locally in memory. Which of these two architectures will produce the fastest response time, given the same data? Sorry? Stateful, right? By an order of magnitude at least, maybe 2 orders of magnitude. The idea behind stateful applications is that the single source of truth is in your application's memory. So you might have a stateless web server that does some work, and it goes and talks to a stateful app server. The app server will go ahead and serve a response available immediately from its own memory, but it'll asynchronously flush and read data from the database server as it needs it. Here's what this model is really all about. We're inverting the role of the database from being the single source of truth that we depend on for every single request to treating it like a dumb backup. That's the idea behind stateful application design. You still have a database, but its role is different. It's just there for recovery purposes now. And so this type of design is capable of achieving speeds that are unheard of in traditional stateless CRUD designs. And this is because we benefit from a principle known as state locality. Raise your hand if you've heard this term before. Okay, good. This will be new then. What state locality refers to is this idea of the data your application needs to run is adjacent in memory to the code that runs it. So this means that you don't have to go very far to get the data you need to do your work. So remember that second scenario I showed you, the real-time event processing? How fast would that be if all of the data for processing those events was available inside the actor's memory who was processing them? It means that's the difference between getting the data you need by looking at a register adjacent to you in memory versus serializing a message, going over the network to a database, having that database read something from disk, serialize it back. You get the idea. State locality allows you to build extremely fast systems. And this is what all these real-time systems tend to use now. So the little stream processing example I showed earlier would only really be able to achieve its goals by leveraging this principle. And actors make that very easy by allowing all the state to be something that resides locally inside it. So that's the idea there. Now, another reason why I bring up state is what allows these protocols we talked about to work. During that consensus protocol example I showed earlier, what's really going on under the hood is that each of those actors who are participating in that operation all have some data about the current state of the object they're modifying and about all the other requests that might be happening in parallel for that same object. Well, here's an example of state at work in a different type of protocol. Who's heard of at least once delivery protocol before? Raise your hand. Or exactly once delivery. All right, cool. Those are protocols that use state to guarantee that messages are received and processed by their destination. So a lot of people who use Akka.NET work in finance, and they're paranoid about a transaction never going through, right? For good reason. Usually they end up losing someone, often themselves, a lot of money if they don't do it. So at most once message delivery requires no state. That's why Akka.NET uses it by default. But the consequence is messages will be lost eventually, as soon as there's a network failure. Well, let's say we want to make sure we have retriable delivery of messages. So we have a technique known as at least once delivery. Well, what we do there is we go ahead and have some state on the sender about which messages we've sent and to whom, and how long has it been since we've sent them. We expect some form of acknowledgement back from the receiver, letting us know it got the message. If we don't get acknowledgement back, we'll go ahead and redeliver the message. That's the state the sender has under this protocol. And as a consequence of that, you might have duplicate messages potentially, but at least you can guarantee that messages are never lost. In an exactly once messaging protocol, we have state on both sides of the wire. The sender has the exact same state it did before in our at least once delivery scenario, but now the sender also has to keep track of which messages it's observed before. This is what's known as an acknowledgement buffer. It has to keep track of which messages it's seen. Because why would you want to keep track of which messages you've seen before under this scenario? What are we trying to avoid? Duplicates. We don't want to process the same message twice. Do you think it might be a problem if we process the same trade twice on a stock exchange? Probably. So the receiver also has to have the state here. So when you design your protocol between these different actors in your distributed system, thinking about the role that state plays is pretty important. Actors still make that really easy. But you just have to sort of exercise a bit of sort of awareness of what you're going to need to make it work. Then the last part we'll sort of close out with here in terms of talking about distributed systems with actors is the CAP theorem. So quick show of hands, who's heard of this before? Okay, cool, about half the room. So the CAP theorem I really think of as just a decision-making framework that sort of offers some trade-offs between different quantities in a distributed system. I think incorrectly, people state that you have these three quantities, C, A, and P, pick two. It's really, in a lot of senses, a little bit more like a gradient to some extent. where you might have some systems that are more strongly consistent, some that are more available, etc. What each of the terminologies mean is first consistency, different than the consistency in ACID. This refers to all nodes seeing the same data at the same time. An eventually consistent system is one where the time between the current state of an object on one node there's some lead time between that and when the other nodes get updated. Availability is a guarantee that every request receives an explicit response. And partition tolerance is the system being able to continue despite arbitrary partitioning due to failures on the network. So that split brain was an example of partition intolerance, right? Essentially, our system wasn't able to tolerate that partition, and as a result, our consistency suffered mightily for it. Well, where this plays a role in terms of this sort of the CAP theorem is it affects the way we design our protocols. Our protocols have to basically be designed in such a way that it takes into account our business's CAP requirements. So, quick example. Reddit. They have a system that basically values being able to serve up content on their homepage no matter what. The vote count that you see in the right-hand corner whenever you look at an article, ever refresh the page and notice that value jumps all over the place? They're an example of a system that really values availability way more than consistency, because they can't serve ads, they can't serve content, and they can't keep users on the site if that ever changes. An example of a system that really values consistency would be a patient record system. Could you imagine a scenario where, let's say you have two members of a hospital staff treating the same patient. One hospital staff member makes a record of a medicine that they just dosed a patient with, and the next hospital worker comes along and can't see that state in the system yet. Could you see there potentially being some accidents that could occur as a result of that? That's an example of a system that values consistency. You'd be way better off having your patient record system go down and force the actual caregivers to talk to each other in real life than you are serving up an incorrect result and having the patient get the same medicine twice, right? So here's an example of how CAP affects our protocols too. On the top, I'm going to have you guys guess which one is higher consistency versus lower. On the top, we have sort of a consensus protocol again, where basically a write comes in for a given entity, and we go ahead and have a couple of actors agree that this write can be done consistently across all three, and then the transaction gets committed at that point. On the bottom, we have a slightly different design, where the protocol basically states that a write can come in, this node will immediately accept it, and then notify other nodes who are subscribed to this information after the fact. This is called a commit and notify model. So, quick show of hands, who thinks the diagram on top is the more consistent of the two? All right, who thinks the bottom one is the more consistent of the two? Who has no idea what I'm talking about? Got a couple of hands, all right. So the answer is the diagram on top is the more consistent, the one on the bottom is the more available. Now the reason why that is, in a high consistency system where you basically only allow a certain, so there's this concept of interleavings of writes in a given system. So quick question for people in the audience who have a relational background. Could I update a record in a database after I've deleted it? Someone want to shout out the answer? No, you can't, right? That's part of SQL's consistency model. The data has to exist in order to be updated. In Cassandra, which is a database with more relaxed consistency requirements, if I have a delete on one node and I have an update on another node, it happen at the same time, let's say if I'm running on relatively low consistency settings, what's going to happen? Well, you shrugged. That's actually the right answer, probably. Who knows what's going to happen? The answer is if the update happened last, that will override the delete. So you basically have this last write wins issue. The idea with consistency is that in that first design, you're going to be unavailable during your update command. You have to give that a negative response. You're choosing not to be available then because that would violate your consistency model. And that's the right thing for that business. But if you're Reddit, you're kind of a little bit more YOLO about it. You just want to serve ads. Doesn't really matter if an upvote overrode a downvote or whatever. That's not really the business that you're in. So the reason why I bring this up, these are the sorts of trade-offs that you want to think about when you're designing the protocols your actors use to talk, to communicate. Is you want to say, okay, what's more important to my business? Do I want to make sure that patient gets exactly one dose of their medicine? Or do I want to keep serving up cat photos and never go down? Like I said, there's no value judgment on either of these, right? These are just quantities you have to balance. What actors help you do is very precisely design these protocols and even test them using stuff like the Akka.NET test kit. The last bit I wanted to touch on is a little bit about fault and resource isolation with actors. So Akka.NET actors follow a life cycle. During the starting phase, an actor will initialize and run its pre-start routine. Then an actor will enter its receiving phase. This is when the actor can begin processing its messages. And let's say the actor stops. It might stop because it was intentionally turned off. You might terminate an actor. Or maybe the actor needed to stop because it crashed through an exception. Well, what will happen in this case is the actor will go ahead and restart in place. And that can happen transparently to everything else in the system. What this allows you to do, and here's where sort of the idea behind the actor model comes in, is you can treat errors locally. In Akka.NET, one of the core concepts behind how actors fail is this notion of, and it's kind of a real life analogy here, parental supervision. Parents supervise their children. So when a child actor fails, the parent will receive a message indicating, hey, your child failed and here's the reason why. What do you want to do with it in response? You might be a tolerant parent. You might go ahead and tell the actor just to restart or to resume, which is effectively a way of like ignoring the error and keep going. Or you might be a parent who is a little harsher and you might kill your child. You might do that. It might harken back to the sort of Roman Empire days there. Or you could also be a parent who believes in collective punishment and you can go ahead and kill all of your children when one of them misbehaves. So there's all sorts of different ways you can treat failure in your system. Typically, you don't see that sort of collective treatment of actors unless the children are executing a cooperative algorithm or something. Mostly you deal with actors one-to-one. But this is an important idea behind the failure models that Akka.NET allows you to detect, is it gives you the ability to deal with errors locally and just restart the parts of your system that failed. So isolate errors down to individual actors, and then either restart or kill them, depending on how severe the error was. This might be the only time in your career as a .NET developer that typed exceptions are actually useful. So yeah, just let it crash is sort of the Erlang philosophy, now part of Akka.NET and Akka. The last thing I'll talk about is detecting network partitions and failures over the network. There's a really important tool that Akka.NET has known as Deathwatch. What Deathwatch is it's an ability to subscribe to another actor's life cycle and know when it dies. There's all sorts of macabre analogies we use in Akka.NET. I guess this one is watch people die. Sort of the idea behind this. So these two actors here are just sort of part of an application I designed. This actor on the right is being watched by this actor on the left across the network. Now, if the server process crashes, this is a type of network failure, right? This is one category of possible failure that can occur on the network where software happens to crash. But what will happen is Akka.Remote will detect that its association to this node is failed. We don't get any heartbeats back from it anymore. So this remote death watcher actor here will go ahead and mark all the actors we were watching on that server as dead. And we'll get a termination notification. And at that point, we can decide we want to try reconnecting back to that node, or we can try connecting to a different node, redirect our work somewhere else. This is the idea of being able to route around a failure. So Akka.NET's sort of built on this idea of being able to react to these sorts of events and just simply redirect our work somewhere else if we need to. So you'll see this show up time and time again in sort of larger distributed systems built on Akka.NET. So what I've tried to sort of give you during this talk is not so much a prescriptive, like here's how you design actors and etc. It's more of here's the conceptual framework for how actors are used to build distributed systems and how I think and how some of the other folks who work on Akka.NET think about how you actually design for these sort of networked applications. Okay, let's say, is that the equivalent of a hook coming to pull me off stage? But the idea behind this is just sort of give you an overview of Akka.NET, what it does, and the concepts that are behind it. One thing I recommend checking out, I don't think I have a slide on this. One thing I recommend checking out is if you go to getaka.net, we have our documentation there. And the last thing we're looking at is go to learn.akka.net. That'll actually put you through Akka.NET Bootcamp, where you'll learn how to write a few Akka.NET applications on your own, sort of using kinesthetic learning, learn by doing. And we've had about 5,000 developers go through that over the past year or so. So definitely give that a try. And if you have any questions about Akka or Akka.NET, I'll stand here and answer your questions. So thank you very much. All right. And do we have microphones for people who are asking questions? OK, cool. Go ahead and raise your hand, and one of the folks will bring one by.
Hi. I have a quick question, actually 2 questions. Does Akka provide a consensus implementation out of the box?
Out of the box, it does not. I've seen someone implement Raft before, and they published a blog post on how to do it. So that's available. But no, we don't have any out-of-the-box components for that.
Right. So the second part of the question is, if we were to build a custom consensus protocol amongst a cluster of Akka nodes, can we dynamically scale out that cluster?
Yeah, you can scale out that cluster. Akka.cluster is just a peer-to-peer network. And what will happen is it uses a gossip protocol to sort of determine when a new node joins. You can basically subscribe to a notification for that. And so you'll receive an event, and that actor, let's say you needed to have the list of all the addresses of nodes participating in a transaction. You can just go and add that to your set if you wanted to.
Fantastic. Thank you very much.
You're welcome.
Hello? Yes, it's on. Cool. So could you compare and contrast quickly to Azure Service Fabric?
So sure. Service Fabric actors versus Akka.NET. Well, I would say one big conceptual difference is that Service Fabric actors kind of adopt a different philosophy than Akka.NET, which is that they try to do a lot of work for you in order to build reliable systems, but you pay for that with overhead and essentially a lot of choices that were made for you by Service Fabric itself. It's a good example. We had someone who was evaluating Service Fabric actors versus Akka.NET. An Akka.NET receive actor can handle about 6.7 million messages per second. Service Fabric was about 140 messages a second. That's one big difference between the two there. And that's because Service Fabric actors are serializing each message and persisting them. It's not because they're inherently bad. They're just trying to do a thorough job of basically persisting everything for you and giving you some reliable state recovery mechanisms. Whereas Akka.NET by default is dumb and fast. I'd say the other thing that Service Fabric and Akka.NET have in common, actually, is if you look at the docs for how the deployment model works, like let's say you want to go and update a reliable service built with Service Fabric actors, that deployment process looks very similar to how an Akka.NET cluster would work. The difference is that Service Fabric gives you the orchestration tools for doing that right out of the box. Whereas with Akka.NET, actually kind of ironically, you'd want to plug into something like Service Fabric to help you do that. So Service Fabric really also has the concept of a runtime built into it, whereas Akka.NET does not. It's just a NuGet package you install into whatever else you're using, whether that's a console app, a Windows service, an ASP.NET application, et cetera. To answer your question? Good. Any others? Any good anecdotes? Riddles? One last thing I should mention, Linux and .NET Core support. The Core Akka library will be available on .NET Core pretty soon. We have an alpha of it already, and we'll be publishing that to NuGet within the next week or so. And we already do fully support Mono. So we have people using Akka.NET clusters on Mono as of a couple of years ago, actually. So we've been supporting that for a while. But we do want to get on top of .NET Core quickly, and so we're working on doing that now. Might take a little while, particularly Akka.persistence. We have to support about 10 different database drivers for that. So that's a bit of a mission, as I guess you guys would say. So, all right, one more question?
Yeah, you have a document database, Azure document database, Akka persistence.
We don't have a document DB driver. We do have table storage and blob for Akka.persistence, but I don't think anyone's done a document DB one yet. No, don't think so. That'd be a good opportunity to contribute, though. All right. Yes?
So just a question. Is there a method of intercommunication between the actors? So for example, you would like to know what is your position as between all other actors processing
So if I understood your question correctly, you want to know if there's some way for actors to sort of broadcast their like telemetry, sort of being able to say like, okay, we're all actors working on this. Out of the box, no. What you can do though, is you can actually go and override some of the built-in like message handlers inside actors and go ahead and basically put some instrumentation in there into one of your own base classes. We have some folks who've had to do things like write auditing systems that are run on top of their actors. And they'll have like a little filter that basically checks to see if this message has the iAuditable flag on it. And when it does, they all perform the special audit action. You can have a special like telemetry tracing action do the same thing if you wanted to. But out of the box, yeah, we don't provide a lot of out of the box tooling for doing that stuff right away, just as part of the keep it simple sort of design, right? Cool, good question. What type of transport do we use? The transport layer is pluggable, but by default we use a TCP transport. So essentially it's a single TCP connection, and it's running on top of a socket server called Helios today. We're going to be redesigning that to use an even lighter weight transport that's designed to be just a simple sort of, I guess we're calling it the network stream transport. It's Helios minus a lot of the infrastructure that it has, and it's designed to be much faster and lighter weight. So the transport layer is pluggable though. The craziest one I've ever seen was we had some Wall Street users who needed to support IBM WebSphere MQ as a transport. Those things, by the way, the licenses for that are about $100,000 a box. So they basically had an existing like auditing system built into that, and they were able to rewrite their transport to use that under the hood. So I've seen that before. I've seen folks do a UDP-based transport before, which is a little bit risky because that message ordering guarantee can't be easily implemented over UDP. And we've also seen people try to do things like a named pipe transport before. I've seen that. Personally, the TCP one is what I've seen like 99.9% of applications use. Keeps things simple. JVM, .NET interop. That's actually been an interesting topic because it's come up on the JVM side a lot too. It'd be possible to do that. The difficult part isn't actually the network protocol, it's actually the object representation. Taking an object, serializing it in the CLR, deserializing it as a JVM object. The way you could solve that though would be something like defining your own Google protocol buffer, where you basically define all the message types that can be interchanged. And that'll solve the object representation problem for you. So that's one approach that we've recommended. You'd also maybe have to customize some parts of the transport a little bit. JVM Akka is moving towards a new remoting implementation that's built on top of Aeron, if you've heard of that before. And that thing is blazingly fast. They're trying to hit 1 million messages per second per connection. They're at about 160,000 per connection right now. So they're still working on that. But that uses, I think, multicast UDP under the hood. So basically a bunch of UDP connections that are multiplexed. So in order for us to interop with that, we'd have to have something that can negotiate the Aeron protocol as well. And there are attempts to port that to .NET today. But I'm not aware of sort of what the progress of those are. Yep. All right, well, I'm actually going to be giving the next talk in this room too. So I'll just stay put here. But thank you all for attending and for the great questions. Thank you very much. Yeah.